Hello everyone, and welcome to Intro to Arduino, the first workshop in a three-part Arduino educational workshop series as presented by the Integrated Teaching and Learning Program at CU Boulder. My name is Lauren, and I'm here to guide you through a series of exercises that make up our self-paced Arduino introductory workshop. To complete this workshop, it's recommended that you have an Arduino kit, which includes an Arduino UNO. Alternatively, you can choose to complete this material using Tinkercad's circuit simulation software tools. To do so, just navigate to tinkercad.com and make yourself an account. Once you're ready, let's jump in. The Introductory Arduino Workshop focuses on introducing you to hardware, software, and the operating principles of our Arduino platform. Today, we'll be learning the basics of inputs and outputs. One quick note, if your kit contains any motors or servos, please avoid touching them today. Those are content for our next workshop, and we want to make sure you're well prepared to protect yourself and your equipment when working with these devices. First, what is Arduino? Have you worked with it before? If not, this workshop will give you all of the tools that you need to get started. If you have, see if you can answer my prompts before I do. Arduino is an open source software that is accompanied by hardware called microcontrollers, designed to work with that software. Open source simply means that it's available to anyone for modifying and sharing, and it's designed with public accessibility in mind. On the right, you see the Arduino software environment, also known as the Arduino IDE. This is where you build the code that will run on your Arduino-enabled hardware. In our case, the Arduino UNO is what we'll be using for this and the following workshops. On the left, you see a variety of microcontrollers that run Arduino software, or were designed to be programmed using it. That doesn't mean they'll only work with Arduino, but that's a topic for a later workshop. So thanks for joining me in learning how to use Arduino, and I'd like you to think about what you want out of this workshop. I want blank to blank. For example, I want my window shades to open when I push a button. Take a few seconds and think about what it is you want to use an Arduino for. It's even better if you have no clue what the Arduino can even do yet, because then the sky's the limit. Here are some examples of projects that are either fully or partially Arduino powered. At CU, the Aerospace Engineering Department has a first-year course that launches balloon satellites that takes their science data using only the Arduino platform. Mo, who's a local Arduino expert here at the ITL program, had a roommate who used some Arduino functionality in their BattleBots robot. Also, if you happen to find your way into the ITL Project Depot, you might look up and see Mo's Cloud, which is a IoT Arduino project. The point is, people all across the world use Arduino for all manners of projects, from engineering to science to arts and hobbies. Throughout this series, I encourage you to keep imagining what you can do, however small or great, using the Arduino. Now that we've seen some projects using Arduino, hopefully you have a better picture of what the Arduino can do, or at least what it is. Arduino does for projects what your brain does for you. It processes data and makes decisions. But what does the Arduino need to be able to do that? The Arduino requires sensors to be hooked up for it to take information, known as inputs, and actuators and indicators to be hooked up to do something, known as outputs. But nothing is more important than you, the person who will tell the Arduino how to listen and act. To do this, you'll need to program the Arduino. That's why the Arduino isn't just a piece of equipment, it comes with a partner. It's software. Its software is a user-friendly set of instructions that operates like a wrapper around the programming language C++. If you've used it before, the style will look familiar. If you're like me, and the first time you've encountered coding is sitting right here in this workshop, you aren't alone, and don't worry, because we're going to start with the basics. So how do we do it? How do we write code? Well, code is an implementation of an algorithm. It's a recipe, just a set of ingredients and instructions in order to obtain a specific desired outcome. For example, what ingredients and instructions would you need to give to a child to turn a light on and off? The Arduino is like the perfect little kid. It will only do exactly what you ask, exactly how you ask it, and it leaves no room for interpretation. You must be specific. And also, unlike people, the Arduino doesn't multitask. It will operate one instruction at a time very quickly. So with our small kid example, you would need to define what a light is, where the light is, how to flip the switch, including how quickly to flip it, how long to keep it on or off, and when to start or stop. See what I mean? It's not quite as simple as, hey kid, go turn the light on. The instructions must be clear and direct, with no wiggle room for alternative solutions. Now let's take a look at some code. I want you to take a minute or so reading through this code. And yes, it is real code that will operate on an Arduino just fine. See if you can't come up with a scenario that explains what this code is doing. Feel free to pause the video right here, and we can pick up with an explanation when you've had a chance to digest what's on the screen. My first question is, did you notice that it is in English? Well, sort of anyway. You can read words. It's not all computer language of ones and zeros. So any guesses on what the code does? Let's start by talking through one of the sections. Can we agree it has two sections? It sort of looks like the code is separated into two paragraphs. Let's start with the bottom section. There are a few more hints in that one. The first line, void loop, open and closed parentheses, followed by an open squiggly bracket, actually called a brace. And as a side note, there's a difference between parentheses, brackets, and braces. Braces are used for grouping statements or instructions, brackets are used for indexing, we'll get to that someday, and parentheses are used for both orders of operation, like in math, and to supply parameters. Back from our side note, void loop, ignore void for now, but loop, we know the word loop. You might think of a circuit, never ending, or over and over again as an endless loop. So whatever's going on within this instruction, shown by our braces, is not only going to happen, but it's going to happen over and over again. Until when? Until we turn off the machine. The next instruction says digital write 13 high. Digital as opposed to what? When I think of digital, I think of watches, and the opposite of a digital clock is an analog clock. Okay, hold on to that thought. What about write? What is happening when we write? We're putting out information. So whatever we are writing, in this case, is in the variety or classification of digital. Now, what is listed after that phrase? Parentheses, 13, comma, high, close parentheses, semicolon. Okay, 13. Well, that's just a number. And high, a school-appropriate term for high, is the opposite of low. It's up. Then our closed parentheses and semicolon. Can we agree that whatever digital write is, it requires two things? The first we saw was a number, and the second we saw was a state of being. We are digitally assigning or writing the number 13 to the state of high. Then, to end our statement, there's a semicolon. Remember, the Arduino can do one thing at a time very well. So just like we end our sentences with periods, we need to end our instruction of code with a semicolon. Keep that in mind, and let's talk through the next line. Delay 2000. Delay. That's a pretty universally understood term. I'd argue that it means wait, or pause, or freeze. When the Arduino gets to this line, it should sit there, twiddling its thumbs, until 2000 elapses. Now, 2000 of what? I don't want to wait for 2000 of anything unless it's quite small. This is where I remind you, an Arduino does one thing at a time very fast. That is the advantage of computing. It can be done at the quantum level nowadays. For our purposes, however, when using the instruction delay, the parameter in the parentheses is expected to be in milliseconds. So delay 2000 is telling the Arduino, wait for a count of 2 seconds. A long time in Arduino land, but a proper amount of waiting in human time, so that we can see what's happening before it changes. The third line is the same instruction before delay digital write, but this time the number 13, whatever that means, is being commanded to be in the state low. I would like you to recall our conversation about digital. Remember, with an analog clock, you can watch every second tick, but with most digital clocks, you see time go from 1 minute to the next. There's no in-between state. I argue that digital write is an instruction that will allow you to assign whatever comes before the comma in parameters one of two states, high or low. Finally, the last line, delay 100, that's how long again? Yeah, 1/10 of a second. Remember, each of these instructions requires a semicolon. It's the punctuation that separates the tasks for our Arduino. Can we agree that 13, whatever it may be, is being set high, freezing in that state for 2 seconds, and then being set low, freezing in that state for 100 milliseconds, before looping back to the first command, being set high, over and over and over again, until it's turned off? Great. Let's address this mysterious 13. Take a look at your Arduino UNO board and see if there's any indicator on the board that jumps out to you with respect to the instructions we just went through. Did you find a 13? I hope so. Did you notice it in any particular category, such as digital, written in white lettering? All of this might suggest to you that 13 is indeed a part of the Arduino board, and it lives in a category that is called digital. So, when the Arduino is given the instruction digital write 13 high, it runs over to the digital category, thumbs through the library catalog for the pin designated 13, and because it was a write command, pulls the lever that sets the state of the pin to high. We've been discussing a collection of dual opposites, digital versus analog, high versus low, and if you've guessed whatever this code is turning something on and off, you'd be correct. So when I'm referring to digital, I want you to be thinking all or nothing. Now that we think we know what's happening in the loop, let's jump back up to the top chunk. Void, again, let's ignore. Setup, parentheses, braces, pin mode 13, output. And that's it. Let's say down the road, you finish your project and are going to display it at an exposition of sorts. How many times do you want to go through the process of setting it up? I imagine just the one time will do for most of us. And that is exactly what's happening in this code. Void setup is code that runs first and only runs once. Then, void loop comes in and runs until instructed otherwise. Let's discuss this instruction, pin mode 13 output. First, remember 13? That was an indication next to a pin on the Arduino. So pin mode is an instruction that requires two parameters. First, the pin in question, 13, and second, the mode of the pin, output. Now, remember what to think of digital? That's right, all or nothing. Two options. If the pin is being used to turn something on and off, or set high and then low, the operative term is set, an action which is being done to the pin. That is why the mode selected is output. You are putting out information on that pin. The opposite of which would be to input, of course, but we'll get to that later. As a rule of thumb, if your instruction is to write, then our mode should be set output. You might be asking me, why do we need this? Well, the fact is you have options. While in the first stage there are only two, high or low, the pin needs to be prepared for the instruction that will be coming. But you only need to prepare it for its task once. That's why the pin mode is assigned in the setup code. No reason to run it over and over again. Finally, the last thing I want you to observe is all of our syntax. The colors on this page are very specific. Teal, green, orange, black. The case of the words as well. Capital M in pin mode, capital W in digital write. This style is referred to as camel case. Last, notice the only uppercase letters in the parameters of the instructions, output, high, and low. Without these subtle changes, your Arduino code will not operate correctly. It is simply syntax, a requirement of the language. The reason is because Arduino recognizes those specific words in those specific formats. Otherwise, you'd have to define what output and all the other instructions mean. Arduino is doing all the work for you. All you have to do is give it the instructions in the way that it wants. So all in all, we've spent a lot of time describing a very simple concept. This code, you may have already guessed, is called Blink, and all it does is blink a light. Soon, or maybe already, this will be a very simple code for you. But if it feels like a lot of information right now, don't worry, it is. This is a lot of information at once. So take a break, stand up or walk around, get a glass of water. Just let it sink in and give yourself a chance to relax. Then good job! You've made it through the first portion of our Arduino introductory workshop. Join me in our next video when you're ready to tackle the next exercise. And we'll actually be hooking up and using our Arduino this time. Thanks for joining me. See you then.